Okay. Good morning, everyone. Thank you for joining with us to the monthly webinar of Charlie. Today, we're gonna have a presenter, Dr. Qiao from WJE Associates. His presentation title will be Decryption of Concrete Durability Deterioration Mechanisms using Concrete Petrography and Image Analysis. Dr. Qiao is a senior associate and petrographer at WJE Associates. He is an associate member of ACI Committees 201, Concrete Durability, and 365, Service Life Prediction. He is a junior editor board member for Journal of Infrastructure Preservation and Resilience. Dr. Qiao received his PhD from University of Science and Technology, Beijing, China. He was a visiting scholar at Purdue University from 2013 to 2015 and a postdoctoral researcher at Oregon State University from 2016 to 2018. His research interests include microscopy of cementitious materials, transport properties of cementitious materials, chemical admixtures, and concrete durability. Dr. Qiao. Here's the stage.
All right. Thank you very much for the introduction, Jialo. So today, I am Chunyu. So I am a senior associate and petrographer and with Janney Elstner Associates. So I am working in the Austin office here down in Texas. So today I want to talk about petrography and its application to durability deterioration. And I don't, the title is about durability of concrete, but I don't want limit my presentation to durability. I will also talk about two cases regarding the concrete quality examination using petrography and other physical testing. So I want to tell a little bit story about who I am. So I'm a proud Boilermaker since Purdue is doing really well in the college basketball game this year. So I'm very excited about their March Madness, journey, in the very short period of time. So I am a geologist and a construction material scientist. So that's what I call myself. So I got a bachelor degree from geology, but since my PhD and so many years, so I have been, working on concrete and different aspects of concrete for a few years. So I am a ACI member, Ryland member, and I also have some activity in the ASTM. So I'm also a junior editorial board member for Journal of Infrastructure Preservation and Resilience. And in the last few years, I published some papers to interact with different engineers, scientists. And as a consultant working in different firms, I have worked on different projects, within the United States and across the globe. So that's about me. So let's dive into the presentation today. So before I get into, the projects or case studies, I want to have a very brief introduction about what is concrete petrography and what do we do in the lab using petrographic examination. So we always think about we are a part of the whole game for concrete and, or structure analysis. So for example, on the top left image, so when you have an infrastructure or a structure, so the owner will notice some problem. For example, this is a hydraulic dam somewhere in Canada. So you can see in the exterior survey and within the structure of this dam, so there are very extensive cracks everywhere, and you see a lot of white exudation, oozing out from those cracks. And along with those cracks, so we see a lot of steel reinforcement corrosion, and we see a lot of concrete covers falling. So this whole structure is a very severe condition that requires a lot of attention, repair, and maintenance. So when an owner identifies the problems and that they want to touch base with some structural engineers to do a very thorough inspection about their structures. So for example, for this case, it is not difficult to identify the root cause for the damage at ASR. So ASR is alkali silica reaction, which will last for years. We call that concrete cancer for a reason, because it is very difficult to mitigate and the whole process is passive in nature, and that can exert a lot of internal stress to the whole structure, eventually, lead to cracks and failures of structure. So that being said, this ASR situation will require, routine maintain and repair to extend the service life, the life expansion of the structure. So during this routine inspection for this structure, the engineers will take course every 5 or 10 years to examine the ASR progress. So for example, on the top middle image here, this used to be a circular core hole. So on a slab within this dam. So after years, so the engineers had to keep saw cutting the slab to release the stress, the expansion. So after years and years cutting, so you can see right now they only have, half circular of this whole core hole left. So just to think about, imagine this kind of dramatic expansion can there's how much, so much damage and stress within the structure. So as I said, identifying ASR is not difficult by Petrography. The question for us, or the most interest for the client, is more about what is the stage of this reaction and how much more damage this ASR reaction can, impose onto the structure. So to solve that problem, to answer that question, a lot of times we will obtain sample cores, from the structure like I showed on the left, on the right top. So after we receive a concrete core in the lab, so we'll do a very thorough visual inspection about the general condition of this, concrete, and after that, so we will, cut a polished surface, over the depth. So this will allow us to see more detailed features on polished surface about what's really going on in this concrete. So for example, if you follow the arrows to the bottom right image here, so this is the polished surface image under a sterile microscope. So we can see there this crack, going out from this cracked or reactive, rhyolite particle into the paste. And you can see part of the crack in the paste has been filled up with, ASR gel. So this identifies the nature and severity of this, the whole ASR, reaction in the concrete. And if we want to see more details, sorry about that, more details, in this concrete, so we can cut a very slice thin, a slice of concrete to make a thin section. So a thin section is really a very thin slice of concrete, which is only 25 microns thin. So it can allow light to go through, so that we can inspect the concrete material in a different perspective. So we can still see a crack, filled up with gel, and we can see the grains within this reactive aggregate particle. So a lot of times, ASR reaction also requires to know the composition of the ASR gel, which can help answer the age of the gel and how long the gel or this reaction has been in place in the concrete. So to answer that question, optical microscopy is not sufficient for it. So we will just throw up a piece of polished, section into the SCM, the scanning electron microscope. So then we can do an EDX analysis together with SCM, observation like what I am showing here. So on the left bottom, so we can see this gigantic crack, is filled up with ASR gel. So different element compositions in the gel can impose different grade levels in the SEM image. So we can do EDX analysis to see if the gel is rich in calcium or rich in alkali, so which can help us identify the age of ASR gel. Together with optical visual inspection, optical microscope, and SM EDX analysis, so we will have a thorough opinion about what this ASR reaction stands within the structure right now. So this will provide useful information back to engineer and clients to together make a decision about what is next step for this structure maintenance or repair, or what's the schedule for the remaining life. So that being said, it's really like in-house, lab materials study and on-site observation. So to thoroughly give opinion to the structures, remaining service life and condition. So what are our weapons and tools when we perform, petrographic examination in the lab? So we have 3 major ASTM standards to follow these days. So the major one, the one in the middle, it is ASTM C856. So this is a standard practice for petrographic examination of hardened concrete. So in addition to the major one, so we have a specific ASTM standard which examine or determine the parameters of hardened air void system in the concrete, which is, sorry about that, which is C457. And for the SEM EDX analysis, we have C4, 1723. So it's a guide for the SEM EDX analysis for concrete. So what are we looking at in the on concrete sample in the lab using using microscopes? So first, we will look at the composition of concrete, which includes coarse airgate, fine airgate, paste matrix, air void system, also embedded objects. And we will also examine the surface defects, surface condition of the concrete, which is super important for horizontal surface like warehouse slabs or outdoor sidewalks or pavements or other structures. And also durability is a big topic these days for everybody to, as to how many years the structure will stand. So we'll examine different deterioration patterns if there's any, such as cracking, spalling, delamination, other, forms of deterioration. So as of chemical reaction, which always involved in the durability issues. So we'll look at what kind of secondary deposits, occupied in the concrete. So the common one is alkali silica gel, ASR gel, and gypsum. Gypsum is an important one for sulfate attack and biogenic attack in sewer environments. And another very last one, but not the least one, is called calcium oxychloride. So which is important secondary deposit in the freeze thaw and de-icer damage we're talking about today. So after we examine different perspectives, different dimensions regarding concrete materials, so we can incorporate what we see to conclude our opinion regarding concrete durability issues. For example, we can literally examine almost all the major topics of concrete durability issues like freeze thaw damage and alkali aggregate reaction, which involves ASR reaction, ACR reaction, or oxidation of iron sulfide, which is more common in the New England area in the States. So for sulfate attack, we can also look at that external sulfate attack. That's like the regular sulfate attack or biogenic attack in the sewer, wastewater treatment plants, or internal sulfate attack, which is majorly delayed etchant formation. So chemical attack can, involve different kind of chemicals. For example, seawater is a common one, and also acid attack, freshwater attack, which involves calcium leaching, and also carbonation is literally for everything that exposed to exterior, atmosphere environment. And in the cold regions in this country, or in many regions in the world, so we use de-icers. So de-icing and anti-icing chemicals can impose the tax as well. So also, in addition to chemical attacks, we have physical salt attack and other different forms of concrete durabilities. So what I want to convey in this slide is concrete petrography can examine different dimensions of the material perspectives and to formulate different opinions to diagnose different concrete durability concerns. So literally this is covered, and a lot of the durability issues are covered in the Master ACA 201 Guide to Durable Concrete. So as I said, I am a material scientist, I'm a petrographer. I always see myself as a team member for the whole game. So we have clients, our clients can be owners, contractors, material suppliers, and attorneys in different cases. So a lot of times, structuring evaluation, material evaluation will involve efforts together, from professional engineers and material scientists. So we have different, lab testing methods. Like I said, we have ASM standards, AASHTO specs, and other FAA specs in different fields. So in addition to those, standards, so I am always down for some new technology that can help us go further mile in the material, testing. So today I want to talk about fluorescence microscopy, image analysis, and electrical resistivity. This kind of new tools, how we can incorporate them with the current testing standards to tackle problem to provide more and richer and more quantitative, information to the clients. So what is fluorescent microscopy? I talked about that in the last slide. So what are we going to do with it in the petrographic examination? Like I said, a lot, petrographic examination in concrete involved thin sections. So what a thin section on the image on the left, we can see, so it's a really thin slice of concrete. So you can use different epoxy with different colors to dye the concrete. So the regular blue dye is a very regular, it's a very standard thin section. So the yellow one on the left is fluorescent dye, thin section. Under regular light, so they have different colors, but we want more than just them looking pretty. So after you shed a UV light or black light to the concrete with the fluorescent dye thin section, so it will glow, but the regular epoxy will just stay dark as it shows on the right in the image. So if we can look at the concrete in different light conditions, especially under this fluorescent light condition, so it can highlight a lot of features that we cannot see from a regular light condition. So that is majorly what a fluorescence microscopy will involve in the thin section examinations. So let's start, with cement chemistry to talk about what we can do, what we can see using this fluorescence dye microscopy in thin section. So we have different Watson ratios in different concrete. So when cement mixed with water, so they will react with each other. We call this hydration. So if we have different water contents in the concrete, so we will have different, pores that will remain unoccupied in future after the concrete is hardened. So we call this part of matrix pores. So if you have a lower Watson ratio, you have a lower porosity. When you have a higher Watson ratio, you will have a higher porosity. So that being said, when you prepare samples, to become a thin section, you will occupy all the pores using fluorescent dye. So that being said, if you have a higher Watson ratio, you have a higher percentage of pore that will be occupied with more epoxy. So if your concrete thickness is the same, so a higher porosity concrete with a higher Watson ratio will glow a brighter green tone because you have more epoxy in the pores. So by examining the different brightness of these green tones, that can give us quantitative information about concrete porosity information, like we're going to talk about in the next slide. So after we get images, yes, visually they will look different, like what I'm seeing here. So a 0.40 Watson ratio paste will look a little bit dark green. If you go up to 0.5, it will become a little bit brighter, green tone. If you go to pretty high, like 0.6, you will see a much brighter green tone compared to 0.40. So that's a visual impression when we look at those photos. But how we can provide more information to the client, in the real, practical or engineering problems in the real project. So these days, image analysis is really popular in a lot of different, subjects and different fields of research or engineering. So an image, let's say here on the right, an image contains million different pixels, X and Y different axes, if we're talking about two-dimensional image. So we can use software to extract the brightness of each pixel in the image to formulate a histogram of the brightness in distribution in this image. So here we see three peaks, for example, the image on the right is histogram of pixels, from the left image. So we can see three peaks at different grade levels. So a lower value means it's darker and the brighter value is brighter. So in the image here on the left, we see a lot of standard particles or black particles, embedded in the whole field of view. So those are standard particles and unhydrated cement particles. So those things are low in porosity. That being said, they don't have a lot of epoxy in them. And when a light goes through the thin section, so that part will remain black because of the lack of epoxy. So that corresponds this sharp peak in the lower range of this grade level distribution. And we also see an air bubble, air void in center. So that's air void. Air void is purely empty. So that being said, it literally has a 100% local porosity. So that will correspond to the small peak on the right, on the high end of this whole distribution. So everything between them, between the standard particles and the empty void, that's our paste matrix. A paste matrix that has a broader grade level distribution, with a peak in the middle. So after we obtain those quantitative information on the right, so we can fit the pixel, the histogram distribution and to get those peak, levels. So that can help us, quantify the change in the capillary porosity among different concrete with different porosities and features. So like I said before, a fluorescence microscopy can examine anything that's occupied by epoxy. The first thing, like I said, in the matrix, so different matrix porosity will come in different grade levels. That's a very powerful tool to examine the water-to ratio of the cementitious material. And if you put this in, if you project the idea to damage concrete with cracks or other open spaces, epoxy can be easily occupied in those cracks and other open spaces. Any features in the picture, in the fluorescent picture with a high contrast, we can use software to automatically extract those information and quantify those features. So here in the next case study, I want to focus on freight thaw damage and de-icing chemical damage, and demonstrating how we can use petrography and other technologies to tackle the problem to help the client decide what's really going on with their deteriorated concrete. So we always know winter is coming. Winter is here. Actually, it's not coming. It's already here. It's almost gone. But the Midwest is going through a very bad windstorm right now. Of course, there is a lot of snow in Minnesota and Illinois and Wisconsin, I believe, after I talked to a lot of friends. So what do we do when we have a lot of snows in the winter on the road? So we still want people to drive. We want people to walk on the sidewalk. So we remove the snow and we apply a lot of de-icers. Yeah, de-icer is very good to keep the traffic open, but de-icers can be really bad, damaging to concrete. So this is a picture on the left, this is just a regular sidewalk I took, outside my hotel in Chicago. So it's a sidewalk with a lot of de-icer. After years, you see those kind of very premature joint damage. So they are, the edges are crumbled and a lot of deterioration occurred. So that's a very typical form in field for freight thaw damage and premature damage due to de-icers. So what exactly is this de-icer damage? What kind of chemical reaction it involves? So we have calcium hydroxide, which is a very common hydration product in hydrated Portland cement. And a normal and more common chloride-based de-icer is, let's say, mag chloride or calcium chloride or rock salt, which is sodium chloride. So if you have calcium chloride, this component in your chemicals, so calcium hydroxide can react with calcium chloride de-icers in a very moisture condition, at low temperature to form a complex salt on the right. We call that calcium oxychloride. So if you look at the chemical formula of this salt, you see it involves 12 different water molecules. So this much water molecules, makes this volume of this complex salt is much bigger compared to the reactant on the left. So it is expansive in nature as of this reaction, just similar to, water turning into ice. So this formation of calcium oxychloride can exert a lot of internal stress to concrete and eventually damage your concrete. So the picture on the right shows a lot of crystals. They are very pretty. It's an SCM image. And yes, they are very pretty, but they're very detrimental to concrete. They're bad to concrete. So here I want to show a picture. I want to say a little bit more before I jump to next slide is. So observing calcium oxychloride is not difficult in the lab, and a lot of research and scientists has created and produced these kind of chemicals in the lab, but it is very difficult to observe in field. So what is the reason for that is, So the moisture change in the environment and the carbonation of this salt, or even the temperature fluctuation, can easily decompose or alter this salt to make it disappear. So that's why it is very interesting that in this case, I observed a lot of calcium chloride in field, and to make the engineer believe it is not an imaginary damage we create in the lab, it is real in the field. So what is this case we're talking about? So this is like a motor supporting slab, under those warning stripes, in a public transit in Colorado State. So after 5 or 6 years usage, in this public transit, this, the owners, the city, invited some engineer to do inspection about the structures, integrity and condition assessment. And after the engineers were on site, they easily, removed those warning stripes and find out the concrete or the mortar, more exactly, deteriorated so severely after 5 winters. And they want to send me a core to examine the condition of the concrete, but they can't even make a core. You can see this guy can easily grab the concrete, in his hand. It becomes so muddy and crumbled. So I only got a few fragments with those kind of crumbled pieces after 5 winters in service of this mortar slab. So this mortar slab has very severe deterioration, very obvious to see after 5 years. And I did a petrographic examination on this case and identified the nature. The mortar is not the best for severe freeze thaw, exposure class. So first, this mortar has a very high Waterson ratio. Apparently, there is no SCM, and that's very alarming for severe freeze thaw dam exposure condition. And also, this mortar did not have, enough or sufficient air entrainment to fight against freeze thaw dam, related, volume change. And also, it has a lot of chlorides inside, because this is a public facility, and they apply a lot of deicers. So after I use epoxy to stabilize those fragments before I kind of polish the surface, so you will see after I kind of polish them and I put them under microscope, we see a lot of those parallel microcrack horizontally. So they are parallel to the exposure surface, and they go around aggregate particle. You can see the standard particle go around them. So this is a very typical feature for freeze thaw dam and slight, deicer damage. And moreover, more than that, if you see closely in those, epoxy occupied microcracks, you see a lot of white deposits. So we will talk about them more in next slides about what they are. So you see this kind of, cracking pattern, and this secondary deposits is very easy to identify the feature of freeze thaw damage and deicer damage. And we also did, chloride measurements on the good mortar and the damaged mortar. So you can see there is almost 7%, acid soluble chloride in the mortar samples I obtained. So that's insanely high. So you can just imagine how much deicer they have used in the past 5 winters to fight to the concrete, to the mortar slab in their facility. So again, we occupied, the cracks, with the fluorescent dye, the epoxy. And after we shed a UV light, you can see all the cracks are highlighted in green, among the, dark background. So after we obtain those images, so we can use softwares to automatically identify or measure the dimension and orientation of those cracks. So then we can formulate a Rose diagram which will indicate a preferred orientation of those cracks. So here we can see, the preferred orientation is more horizontal from 290 degrees, through 90 degrees. So that is exactly what we are looking at visually. So in addition to those easily identified orientations, so more importantly, we can measure the width and the length of those crack fragments in different locations, and we can measure and quantify the crack density and crack area to see how much stress and expansion has occurred, in different locations. So you can see, outer zone and inner zone in different mortar, samples are different, and upper zone, lower zone, I'm sorry, they're kind of confusing labeling. That being said, different location, different depth of mortar will show different damage, and we can quantify that. That's powerful. A lot of petrographers cannot provide this information without fluorescent microscopy. So that's why I like fluorescent microscopy so much, to give me more numbers to help engineers and the client better understand what they're looking at. So after we talk about the damage, as I said, secondary deposits are also very important for us to identify or characterize the damage. So after I obtain these samples, you can see there is a very thin crust, white crust, the secondary deposit on top surface of this mortar sample. So that's a blend of brucite and calcite due to carbonation application of chloride in their concrete. So other than that, on the right, we can see I just induced a fresh fracture by my hands because it's so soft. So we see a lot of clear crystals in different shapes. So yeah, we have different shapes. They're all transparent, but we cannot really tell the chemical composition by our eyes. So what do? As I said, we throw the samples into the SCM chamber and look at them under SCM EDX conditions. So here, the image on the left is a fracture surface. You can see in the middle, that's an air bubble, or I want to say that's an air void. So you can see this air void is filled up with different shapes of secondary deposits. So we can identify 3 different kinds, A, B, C, as indicated in the image. And after we get the elemental composition data on the right, we can see, the image, the crystal A, it is high in oxygen, chloride, and calcium, which is a very typical elemental composition for calcium oxide, as we mentioned about. And the B, the needle shape and the chemically rich in alumina, sulfur, and calcium, that's typical for etchingite. Etchingite is a very good indicator for elevated moisture condition in the concrete. So what is C? So you can see C is high in oxygen and calcium. There is barely, aluminum or silica or sulfur chloride inside. So that is a very typical calcium hydroxide crystal, elemental composition. So in this one single void, so through petrographic examination, so we can identify different natures of the secondary deposits. So why do we have calcium hydroxide in a void? So what does that mean? That means when we think about the chemical reaction between the calcium hydroxide and calcium chloride in the deicer, so it has an effect of calcium leaching, which will extract, the calcium hydroxide, pull this calcium hydroxide from the matrix to the air void to form this calcium oxychloride. So how can we tell the alteration in the microstructure in the chemical composition of the matrix? So here are some thin section images, under the light mode. We call that cross polarized light with gypsum plate inserted. So yeah, that name sounds pretty fancy, but we don't really have to focus on those terminologies because that's my job to do it. So what I want to point out here is, if you compare the good mortar, damaged mortar here, so those oranges or blue, shape, shapes of different, those shapes, they are crystals, calcium hydroxide crystals. So in a good mortar, so you will see those calcium hydroxide crystals evenly distributed in your hydrated cement paste matrix. But after the deicer damage on the right, you can see here, you barely see those calcium hydroxide. So this is a direct evidence or indicator of calcium leaching due to the deicer damage, due to the formation of calcium oxychloride, these crystals. So again, as long as we have high contrast features in the images, we can ask the software to quantify those areas and tell us the content, the volumetric content of those features in the field of view, and then help us quantify the calcium leaching we're talking about here. So we can tell almost 90% of calcium hydroxide has leached out due to the deicer exposure. So this is very significant. Just think about that. So calcium hydroxide is a solid component in a concrete matrix. So it easily account for 20% of volume of the total cement hydrates in the concrete. So if you have almost all the calcium hydroxide leached out, so you're losing content, solids into, from your matrix, that will make your concrete weaker in mechanically and more porous for external fluids or substances go into your concrete. So that's an indication of calcium leaching, just to use, standard petrograph, microscopes. And also we want to look at, okay, so your concrete is losing calcium, just like your, humans' bones are losing calcium. That's not a good thing. So how can we tell how more porous your concrete is? So again, under a regular light, thin section observations here, the good mortar, bad damaged mortar, to me, they look very, very, very similar. Unless you have a magical pair of eyes, probably you can tell the difference, but to me, they're very similar. So how can we tell the microstructure, the porosity has changed? Again, put them under the fluorescent light mode. So we can see the good mortar has a little bit darker grain tone compared to damaged mortar's matrix. So when we apply those image analysis, as I mentioned before, so we can easily extract the grade level distribution in two images, and we can see the middle peak representing the cement matrix paste, porosities shifting from a lower peak to a higher peak. So this can help us to say, okay, your capillary porosity has roughly, let's say, 15 to 20% increase, which corresponds to the calcium leaching that we examined from the previous purple or orange or blue colored images. So here in this case, I just wanted to show everybody that, so as a petrographer in the lab industry, so we can use different tools, use different light modes from the microscope to tackle the problem, to explain or try to extract as much information as we can to convey that information back to the engineer, the owner, to help them clearly identify, characterize their problems. So that is very vital information for them to decide what is next step. So that coincides with what we call here, infrastructure, durability and life extension. So that happens every day in field. That happens every day in my work, every day. So that is a, durability. Let's say that's a durability case study. So next one, I just want to go very quickly about another case study about fluorescence microscopy, how we do that to tackle the low strength issue. So a lot of times if you have low strength issue, it involves elevator Watson ratio or air contents variation. So this is a facility in North Carolina, is exterior slab on ground. It was constructed in the summer of 2022. So the design strength for this exterior slab on ground is 3,500 PSI with a Watson ratio of 0.457, which is really high. And a 1.5% air content, I believe, is in North Carolina. We don't have a lot of free cell cycle. They don't really require a rate airing treatment. So even for 3,500 PSI design PSI, strength, the measured strength for the actual slab is, it was only as low as 2,500 PSI. So that's even like 1,000 PSI lower. So the clients want to know what's really going on with their concrete and why the low strength is there. It's present on their concrete. So obtained different cores from different location slabs. So they have the strength varied from a standard, almost a specified strength like 3,500 PSI to a 2,580 PSI. So you can see the color of the paste under a stereo microscope. They look kind of different. So it looks, from a light gray to a white color. So the color difference is not really that significant under microscope. So how can we tell more, using the fluorescence microscopy? Again, in the thin sections, we cannot really tell the difference. We kind of see the a little bit more porous under the 200, for the lowest strength core, but how we quantify that? So if we observe the thin sections under the fluorescence light, so you can see the grain tone change from a darker green to a brighter green tones. So I want to emphasize that. So the sample preparation for the thin sections are very important. It's very important for comparative analysis, such as what we're doing here. So we want to make sure the thin sections were made in exactly the same thickness and also with the same epoxy dye concentration, the dye concentration in the, the dye concentration in the epoxy. So after we, calculate the apparent, capillary porosity using those image analysis from the grain color image. So we can see different numbers here, of this capillary porosities. They are not real capillary porosities. I would rather call them apparent capillary porosities, just calculated from the fluorescent microscopy. So you can see those numbers corresponds really well with the strength loss, which is understandable. If you have a higher Wilson ratio, you have a higher capillary porosity, which will make your concrete, concrete matrix more porous and less densified. So of course, it will have a lower, compressive strength. So this is just a small case that we indicate how we can use concrete petrography with fluorescence microscopy to tackle this concrete quality issues for new constructions. So I know I'm getting my time limit here, but I also want to go through another thing I'm very interested since my PhD is how we can use concrete, electrical resistivity to identify or characterize concrete quality together with concrete petrography or to facilitate petrographic examination. So electrical resistivity information factor, that's the ASTM standard right now. We call them 1876. So formation factor is not really a mandatory measurement in this ASTM standard. It's more a concept, and then that is written in the commentary in this ASTM standard. So here I just want to focus on electrical resistivity. Concrete conducts electrical resistivity, as we know. So why? So rocks and sand, they do not conduct any solid, they do not conduct electricity. So it's only the pore solutions, more exactly. The pore solution in the matrix pores, they are the medium to conduct electricity by the mobility of the ions inside. So we have alkalines, with ions, and we also have hydroxide ions and other, minor components of ions in the pore solutions. Those are the medium which make concrete conduct electricity. So that being said, if we have different porosity, have different pore tortuosity, those kind of different features of pore networks, so the electrical conductivity can be different because so it will go through a more tortuous or less tortuous space or path in a higher porosity or lower porosity. That will give a different concrete bulk resistivity. So pore network is really important for durability issues because almost all the external substances are the causes or the root causes for all kinds of concrete durability issues. So external substances, we have moisture, we have chlorides, we have sulfate, we have CO2, we have all different kinds of external substances. They can only go through the pores in the concrete, into concrete to interact with the components of concrete to induce concrete durability issues, such as free thaw, that's moisture, and corrosion, then chloride, sulfate attack, then sulfate, and ASR. Even ASR is a reaction between alkali and siliceous components within the concrete, but it requires external moisture to let this occur. So CO2 is very easy to understand. That's carbonation we're talking about almost every day. So the key is pore network, as I say. So you have different ways to measure concrete resistivity. So you have the surface resistivity measurement on the left. You have the bulk resistivity. That's what we normally do in this ASTM C1876. And you can even put rods in the precast cylinders. So that's very special setup, for lab use. So, but that's not a standard test. The standard test is in the middle and on the left. So we also call, ASTM C1876 myself like a bucket test. So why do we call them bucket tests? Because you have those concrete cores or cylinders, and you make simulated pore solution in a bucket, and you submerge those concrete samples into this pore solution, simulated pore solution in the bucket. After 5, 6, or 7 days, you get them out, you mop them surface saturated dry, and you measure the resistivity. So it's just how easy that is compared to, other forms of, durability measurement, let's say RCP test to indicate concrete quality. ASTM standard C 1876 electrical resistivity is much easier compared to RCPT test. And it is more physical meaningful compared to RCP's, column numbers. So we have this tool, in our hand. So like a lightsaber, so we can be a good guy and we can be a bad guy. So what are we going to do? We want to be a good guy and we want to use electrical resistivity to help us solve problems, especially here, give a case for concrete quality. So this is a rain damage case. So what it is about is interstate highway bridge span in Utah. So this general contractor poured concrete, during a very sudden thunderstorm. So UDOT wanted to rip off all the 3 spans. Of course, the contractors and the UDOT, they want to know what's really going on with the concrete and what's the rain damage extent, if there's any. So rain damage is very common. It's not very common. It is an issue that arises when your concrete is placed and finished during a heavy rain event before the concrete is set. So, for example, if rainwater is finished in the concrete or enter the top surface of concrete, so it will change the elevator's water ratio on the top surface to make the top surface more vulnerable to abrasion and compromise other durability problems like freeze-thaw damage or cracking or other forms of durability concerns. So normally, rain damage is not very deep within concrete compared to the total thickness of the concrete. For example, here in this case, the rain damage is only the top, let's say 1/8 inch to 1/16 inch, say, compared to the whole 8 inches concrete that's really limited on top surface. So what can we see using fluorescence microscopy between the top and middle of the concrete? We can see a big change in capillary porosity change. So the left is the top concrete surface, and the dark green tone matrix that's from the middle of the concrete core. So we also did compressive strength. Like I said, the rain damage is really limited within top surface. So the 3 spans, span 1 is controlled without rain damage. We can see all the concrete cores from 3 spans, they show very similar compressive strength, around 8,000 PSI. So that being said, overall quality of the concrete is not seriously affected by the rain damage. So the electrical resistivity, like I said, is indication of poor structure and also the durability of the concrete. So they have very similar numbers. That means the concrete will just perform as is compared to the, as the control concrete. So that being said, in this case, so we don't really need to rip off the whole spans of the concrete slabs. So what we are gonna do is only to remove the rain impacted surface layer and apply a topping, abrasion topping, to strengthen the surface condition. So again, those are 3 cases I want to share with everybody today regarding how we want to use petrography together with other technologies and tests to tackle real problems in the field other than just scientific research in the lab. So fluorescent microscopy and image analysis are really helpful in my mind, and they're beneficial in semi-quantifying and quantifying microscopic features such as crack density and microstructure alteration. And of course, we want more efforts, in collaboration between engineers and petrographers in the community to better, serve the clients, solve their problems. Especially these days, new technologies emerge, this chat GPT or AI thing is serving, and who knows the future, how they can help us, as a powerful tool in the lab, and how they can help us to restructure, our, forensic investigation community in this country and in the world. So thank you very much for everybody's attention. So that is my presentation. So any questions? So just ask me. Thank you so much. Thank you, Qiao. That's my presentation. Yes.
Thank you, Dr. Qiao. It's a very wonderful and impressive presentation. Actually learned a lot. So if anybody have any questions, just feel free to ask Dr. Qiao or type in the chat box. I think we've already got 2 questions.
All right.
The first one is that nice presentation. Low water to cement ratio means lesser pores and higher water to cement ratio chance to introduce higher. What is the relationship on the pores when we use low water to cement ratio with water reducers?
So if I understand correctly, so this is like if you have a low Western ratio concrete, so yes, you have less pores, and you have a higher Western ratio, you have higher pores. So if you have the same Western ratio, but you have different water reducers, so the water reducer does not really necessarily or essentially change the porosity of the concrete. So that being said, the usage of water reducer cannot really change the greenish, let's say the green tones under the fluorescent microscopy. So, but one thing we have to keep in mind is sometimes water reducers can really alter the hydration, especially in the early ages. If we use, petrographic, fluorescent microscopy to look at early age, low water ratio concrete with, different kind of water reducers, we need a lot of background information from the engineers to really tell us what we're looking at. So again, that just goes to my remarks, is a strong collaboration between the engineers and petrographers together to analyze what we're looking at, what we're seeing, and how to properly interpret it.
Okay, the second question is that slide 19. Could you explain how deicers introduces elevated temperatures leading to aggregate formation on point B?
I don't think did I say something like that? I don't think I said something like that, but let me go back to slide 19. Yeah. So it's not, so explaining deicers. Deicer does not really introduce any temperature change. Temperature changes of environmental parameters. So here I literally just want to introduce different kinds of secondary deposit and the void. So it doesn't really involve any temperature change in this picture. So B is etching guide formation. Like I said, etching guide formation is moisture change. It's not a temperature change. So a lot of times if we have a bad slope design, so that means if we have a lot of, let's say, deicer containing runoff that just to keep staining on the top surface of those structures horizontally. And those moisture can penetrate the concrete to introduce extra, elevated moisture content. That's why we see etching guide formation. I think Precious can just contact me if he has more questions regarding the elevated moisture content instead of rather than elevated temperature content for the etching guide formation. So I don't think temperature is a big influencer, for external etching guide formation. That's more a factor as of the delayed etching guide formation. That's another topic. I mean, for the formation, right? So we can talk about that later in details, after the presentation.
Okay, yeah, actually, I may have one further question about the water reducer and pores. So I'm not quite sure what do you mean that there's not really a significant influence of water reducer on the pores? Is that in the pores that you talk about, is that all types of pores or some specific types of pores? Because based on my previous experience, that water reducers may, especially in self-consolidating concrete, the usage of water reducers, the entrapped air voids and entrained air voids may both get increased a little bit.
Yes. Yes, Diallo. So when I talk about the process here, I'm not really talking about air voids. I'm more talking about the matrix pores, gel pores, cavity pores, those things, between the hydration product. So yes, if you have chemical admixtures, that will change big time, not big time, very commonly change the air entrainment or air entrapment, right? So those air voids are not really the pores I'm talking about in those slides. Those slides are more like, the gel pores or cavity pores in the matrix. So like I said, if you have water reducers, especially for SCCs, as such, special application, you use all the different kinds of admixture, shrinkage reducing or viscosity modifier, or water reducer, all those kind of things, or slump changer. So all those things will change the early age performance or behavior. Is more rheology, and the first few days, the hardening, the setting, all those things that I said. If we're looking at early age concrete with different extended hydration, that goes to different hydration degrees, right? So when I compare different Watson ratios in those in those slides here, I'm talking in those cases, they are mature concrete after well cured or in service for a long time. So I just assume they have reached their maturity, let's say, their degree hydration normally and those Watson ratios. So then you can compare. So again, if we just look at the same Watson ratio and different age of hydration from day 1 to day 7 to day 28, you will still see different porosity change, different grain colors, because your porosity changes, evolves, and the Watson ratio as hydration proceeds. So I don't know if I have explained it or not. Yeah.
Yeah, I think you did. Yeah. Thank you. Any more questions for Dr. Qiao? No? Okay. Yeah, Dr. Qiao, maybe you can finally get to the first page to show your email address so that people may get to
Okay.
know.
So my email address actually,
And contact after.
yeah, at the bottom. So
And we'll have the video recording of this webinar available on our website and YouTube channel probably in a week. And just feel free to watch the videos if you want to review something. Okay.
awesome.
Cool. So again, thank you everybody for joining this webinar, and thank you, Dr. Qiao, for your great presentation.
You're welcome. Thank you.
Wish you guys all have a nice day, and bye-bye.
Thank you very much, everybody. Have a good day or evening. Bye-bye.